Okay, so let's say that we have a 100-meter race. And in this 100-meter race, let's say it's the finals of the Olympics, there are 8 runners. And of course, there's 3 winners. There is the person who gets a gold, the person who gets silver, and the person who gets bronze. And all of the other people don't medal. So let's mark them in. So 5 people don't medal. And we're asked, well, how many different ways can there be medalists? For example, maybe runner 1 wins the gold, runner 2 wins the silver, runner 3 wins the bronze. That's one way. Or maybe something along the lines of runner 4 wins the gold, runner 2 wins the silver, runner 7 wins the bronze. There's another way. How many different ways can there be medalists? So, if we think about this in the right way, we can translate this into an arrangement of symbols problem. So if we think about it, there's 4 different states that the runners can be in. The runner can win the gold medal. The runner can win a silver medal. The runner can win the bronze medal. But remember, we just care about the medalists, so whether they come 4th to 8th, we don't want to differentiate them. So we just say they do not medal. So let's use the symbol X to represent that. And if we think about it, we can arrange 1G, 1S, 1B, and 5 X's into a word, and that arrangement will give us the placement of the gold, silver, and bronze. Let me give you an example. So if we had something like this, so here's a word, and it looks like we have XXBS, XXGX. Now what is this telling me? So this is telling me that the first runner didn't medal, the second runner didn't medal, the third runner won the bronze, the 4th runner won the silver, 5th didn't medal, 6th didn't medal, 7th runner won the gold, and the 8th runner didn't medal. So you can think of the placement as which runner. So the placement of the symbols tells you what runner places what state each runner is in, whether they win the gold, silver, or bronze, or don't medal. So any arrangement of these gives us a different medalist. Gives a different medalist order. This one again, the 7th runner wins gold, the 4th runner wins silver, the 3rd runner wins bronze. Another one, let me do one more. Something like, let's do S, X, X, G, X, B, X, X. So what does this tell me? This one tells me the 4th runner won gold, the 1st runner won silver, and the 6th runner won bronze. And the other 5 runners, the 2nd, 3rd, 5th, 7th, and 8th, did not medal. So any arrangement of these letters gives us a new medalist order. So we have to ask, how many different arrangements of these letters are there? Well, we know how to do this from the previous video. So the number of arrangements there are 8 letters in total, so 8 factorial up top, and we have to divide by the factorial of the number of each symbol. So here we have 1 gold. I'm just going to put this in, but you don't really need to. 1 gold, 1 silver, 1 bronze, and we have 5 X's. 5 did not medal. So we divide by 5 factorial. So let's simplify this a little bit. And when you have kind of numbers in the denominator, factorials in the denominator, that are smaller than factorials in the numerator, this might be a good idea to help you simplify it. Well, rather than writing 8 factorial as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, I'm going to write it as 8 times 7 times 6 times 5 factorial, because 5 factorial is, of course, 5 times 4 times 3 times 2 times 1. And then I can easily cancel that out with the 5 factorial in the denominator. So this factorial cancels out with this factorial, and we're left with just 8 times 7 times 6, which you can work out with a little multiplication as 336. So there are 336 different ways that these 8 runners can medal. And this is a very powerful technique, treating these kind of counting word problems, how many different ways of something, where you're counting how many different ways a bunch of things can be in different states. This translating it to an arrangement of letters problem is very powerful. Let's do a few more examples. Well, let's look at this one. So there are 10 employees, and a boss wishes to form a committee, and that committee has 3 employees on it. There's no special roles on this committee, it's just 3 people on the committee. And we want to know how many different committees can the boss form. Well, one committee would be something like the first employee, the second employee, the third employee. Another committee would be the first, second, and fourth employee. So there are 2 different committees. Any committee that has different members is a different committee. So maybe pause the video now and think about what possible states these employees can be in and how many of them are in each state. Remember, every employee has to be in one state. So once you determine your states, the number in each of those states should add up to 10. Okay, so really, there are only 2 states here. So let's use a check mark to mean on committee. So either employee is on the committee, and we'll use an X to mean not on the committee. And how many check marks are there? Well, there's 3 employees on the committee, so there will be 3 check marks. And there are 7 employees not on the committee, so there will be 7 X's. So any arrangement of 3 check marks and 7 X's, or maybe you use different symbols, there's nothing special about check marks and X's. Maybe you used C for committee and X for not on committee, or maybe used A and B. Maybe you used smiley face and frowny face. It doesn't matter, just whatever 2 symbols. And just as an example, well, something like this, if I wrote down check, X, 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 check, X, 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 check, X, this is telling me that employees employees 1, 5, and 9 are on the committee, and the others are not. And others are not. So, just like before, any arrangement of these 10 symbols, the 3 check marks and 7 X's, that will give us a new committee. I'll do one more just as an example. So if we have X, 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 check, 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 X, 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 this tells me that employees 4, 5, and 6 are on the committee, and the other employees, 1, 2, 3, 7, 8, 9, and 10, are not on the committee. So this is employees 4, 5, and 6 that are on the committee. So again, any arrangement of these 3 checks and 7 X's gives us a new committee. And we know how to count arrangements of different symbols. So let's write down number of committees. And to count these, it's simply the number of symbols, factorial. So actually we can write down 10, since we know how many symbols there are. There are 10 symbols, so 10 factorial. And we divide by, for each state, the number of objects in that state, or we could say the number of symbols that repeat. So here, the check mark repeats 3 times, so we divide by 3 factorial, and the X repeats 7 times. There are 3 check marks and 7 X's. So let's simplify this a little bit. 7 factorial is the bigger factorial. So I'm going to write 10 factorial as 10 times 9 times 8 times 7 factorial. That'll let me cancel off a lot of things. So I get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All of that is in this 7 factorial. And we're going to divide by 3 factorial, 7 factorial, and our 7 factorials cancel. So we have 10 times 9 times 8 divided by 3 times 2. And remember, a nice feature about these, again, it's a little beyond the scope of this class to show you why, but everything in the denominator will cancel. So I have a factor of 3 in the 9, so let me cancel that out. 3 divided by 3, oh, wrong pen. 3 divided by 3 is 1. 9 divided by 3 is 3, so we factored it a 3 from the 9. And let's factor it a 2 from the 8. So 8 divided by 2 is 4. And the reason I did that and didn't take it from the 10 is because it's really easy to multiply by 10, so I don't want to kind of mess that up. It wouldn't be wrong if you did that, it just might be a little more work. So we're left with 10 times 3 times 4, and you could easily see that that is 120. So there are 120 different 3-person committees that you can make from 10 employees. Okay, let's look at these 3 problems that are quite related. So we have a 4-digit number, and I'm going to say the 4-digit numbers cannot start with a 0. So let me mark that down. 4-digit numbers cannot begin with a 0 as a digit. So we don't want something like 0, 1, 0, 0. Because really, 100, you wouldn't write a 0 before that. We wouldn't call that a 4-digit number. We'd call it a 3-digit number. So that's what I mean here. All right. Let's look at part A. So this isn't particularly bad, but I do want to show you some different ways of approaching this. So let's look at A. And let's make sure we understand what this looks like. So something like 7, 2, 1, 4, that's something we want to count because it has exactly 1, 2. Something like 2, oh, let me do it in black actually. Something like 2, 4, 9, 2. We don't want to count this because it has 2 2s. Or we don't want to count something like 3, 4, 7, 0 because that has 0 2s. We want exactly 1, 2. So, if you were trying to explain how to come up with a number with exactly 1, 2, what would you tell somebody? So maybe pause the video now and see if you can come up with a recipe for developing one of these 4-digit numbers that have exactly 1, 2. And then we'll talk about how to count that. Okay, so the way I would approach it, maybe you would approach it a little differently, but the way I would approach it is you have your 4 digits, you put the 2 in one of them, so really you have 3 spaces and 1, 2. So you put your 2 in one of these 4 spots, and then once you do that, that 2 is fixed, and then you ask, well, how many choices for the other digits do I have? Well, here I can't put a 0 because that's the first digit, and I can't put a 2. So how many digits do I have left? I have 8 possible choices. Remember that once I use a digit, I can use it again. So something like 1, 2, 1, 1 is fine. That is fine. Okay. So I have that. What about this digit? Well, it can be a 0 now. I can have zeros after the first digit. So the only thing I'm not allowed is a 2. So there's 9 choices there. And same with here. There are also 9 choices. You're not allowed to have a 2 there either because we want to have exactly 1, 2. So if the 2 appears in the middle spot, then you have 8 choices for your first digit and 9 choices for your second digit and 9 choices for your third digit. So if the 2 appears in the second digit, then you have 8 times 9 times 9, which is 8 times 81, which is, let's write that down, 8 times 81 is 648. So in this instance, there are 648 different numbers, where the 2 is the second digit. But the 2 can be any digit. It can be the first, second, third, or fourth. So we have to do some different cases. So the 2 can be the first digit. If the 2 is the first digit, and really I should have been a little more ordered with this. I should have probably went first, second, third, fourth for where the 2 is, just to keep things organized so I didn't miss a case. But let's do this. So we have a 2 in the first digit. Well, for the second, third, and fourth digits, the only restriction we have is it can't be a 2. So we still have 9 choices for each of those guys. 9 times 9 times 9. So we have 9 choices for the second digit, and 9 choices for the third digit, and 9 choices for the fourth digit. And they're all independent of each other. If I pick one, it doesn't affect my choices for any of the others. So this is just 9 times 9 times 9, and you can check. This is 729. So we have 729 4-digit numbers that look like this, where there's a 2 in the first digit and some other digits that aren't 2 in the second, third, and fourth digits. Okay? And if I'm thinking about it, there's 648 choices when the number looks like this, but the number can look a different way, or it could look like this, which means when I'm counting the number of choices, I'm going to add them. But, of course, there's two more ways. We could have it look like this with the 2 in the third digit. So this is 8 choices for the first digit. It's not a 0 or 2. 9 choices for the second digit, not a 2, and 9 choices for the last digit. Again, I can't pick 2. So this is 9 times 9 times 8, which is, of course, 648. Or the number can look like this, with a 2 as your last digit. And again, same logic applies. 8 choices for your first digit, 9 choices for your second, 9 choices for your third. This is 648. So the number can look in any of these ways. So we can look where we pick the first digit that isn't a 2, pick the third digit that isn't a 2, pick the last digit that isn't a 2, and make a number that looks like that. Or we can pick the second, third, and fourth digits not being a 2, or the first, second, and fourth, or the first, second, and third. So, using our rules for the additive and multiplicative principles, all we have to do, let me make a little bit of room here, is add these together. 648 plus 729 plus 648 plus 648. And we get 2,673 different 4-digit numbers that have exactly 1, 2 in it. So that's pretty cool. Let's move on and do the other 2 problems. So what about 2 2s? Well, here, let's think about arrangement a little bit. Really, what we're doing is we're arranging 2 blanks and 2 2s to make kind of a blueprint for a number. Because in any number, there's going to be exactly 2 2s, and the blanks can represent any digit that isn't a 2, except unless it's the first, then it has to be not a 2 and not a 0. But let's make sure we get all of the possible arrangements by counting via our arrangement of symbols things, because we have 2 blanks and 2 2s. So we have 4 symbols, we have 2 blanks and 2 2s. 2 plus 2 is 4, so we've covered all our cases. And I'll leave it as a small exercise, but this simplifies to 6. So there are 6 different arrangements of 2 blanks and 2 2s. So let's try and count them all. We know we need 6 of them. Let's see if we can get them all. So I'm going to do it in order. So there's 2. Let's have the 2s first. 2 2 blank blank. And then I'll keep moving 1 2 as far as I can go. So I have 2 blank 2 blank, and then I'll have 2 blank blank 2. Okay, so they're all the possible kind of blueprints for my number that start with 1 2. Well, what about the ones that don't? Well, let's have the ones where the first digit isn't a 2, but the second digit is. So we have blank 2 2 blank and blank 2 blank 2. So we have all of the ones that have the first digit as not a 2 and the second digit as a 2. Okay? And then we just have the case where we have neither of the first digits as 2s, but the third and the fourth are. And we check, we have 1, 2, 3, 4, 5, 6. That's exactly what we expect. We have them all. That's good. So these are all the blueprints for our numbers that have exactly 2 2s in them. Okay? So, how many choices do we have for each? So, here we have 2 2. There are 9 choices for the third digit because we're not allowed a 2. We get to be a 0, 1, 3, 4, 5, 6, 7, 8, or 9. That is 9 digits left. So there are 9 choices. And we have to pick a fourth digit, still 9 choices. So how many different 4-digit numbers start with 2 2s? That's 9 times 9, which is 81. And again, same here. And the second and fourth are not 2s. There's still 9 choices for those. That's another 81 4-digit numbers that look like 2 blank, 2 blank. And similarly for the ones that look like 2 blank, blank, 2, there's 9 choices here. So that's another 81. And what about blank, 2, 2 blank? Well, here, there are only 8 choices for the first digit, because not only are you not allowed a 2, but remember, you can't start with a 0, too. You can't start a 4-digit number with a 0, because then it's not really a 4-digit number. It's like a 3-digit number or fewer. Maybe it's a 2 or 1-digit number, but it's definitely not a 4-digit number. So it's not 0, not 2. There's only 8 choices. And there are 9 choices for the final digit, the 4th digit. Notice I said the word and. So we multiply. 8 times 9 is 72. And remember, when we do this procedure, we broke it down into cases where our choices are independent. Whatever digit I pick for the first digit does not affect my choice for the last digit, which is great. So I broke up my counting into a bunch of cases where my choices are independent. That is a key thing. Okay, let's keep going. So same thing here. Can't be 0, can't be 2. There's 8 choices left. In the third digit, can't be 2. That is 72, 8 times 9. And similarly, in the last case, 8 times 9 again is 72. So the way my number can look is 2, 2 blank blank, or, so we'll add 2 blank, 2 blank, or, and we keep going like this because this is how our number could look. These are all ors here. So we add all these together. So 3 81s plus 3 72s. So let's just do this very quickly. So my 1's digit is 9. My 10's digit is 8 plus 8 plus 8 is 24. 7 plus 7 plus 7 is 21. 24 plus 21 is 45. So there are 459 two-digit numbers with exactly 2 2s. Great. Okay, let's do the third one. So, this is at least 1 2. So what does this mean? And there's kind of 2 ways to approach this. One way is going to be a little more difficult. The other way is going to be a little easier because we only have to count one thing. And in fact, we've already counted it. So maybe pause the video and think of how to calculate this. There's 2 ways, and I'll explain both. But pause the video now and think how to calculate it. Okay, so the 2 ways you might have come up with are the first way, and this is kind of the long way. So count the ones that have exactly 1 2, and then exactly 2 2s, and then exactly 3 2s, and add exactly 4 2s. In terms of being correct, this would absolutely be correct. If a 4-digit number has at least 1 2, it either has 1 or 2 or 3 or 4 2s in it. So you could do it like this, but you can imagine this being a lot of work, especially if we didn't do the first 2 parts of it already. So we could be a little more clever. So this is way 1, which is kind of not particularly clever. But way 2 is quite clever if you think about it. So what it is, well, another way of wording this is instead of at least 1, 2, we can say how many 4-digit numbers don't have 0 2s. So a rewording of this is do not have 0 2s. Which means there's only one thing we need to count. We need to count the 4-digit numbers that have exactly 0 2s and then subtract it from the number of all 4-digit numbers. So that's our second plan. So our counting becomes a little bit easier. So it's, let me do this in black actually, all 4-digit numbers minus the ones that have exactly 0 2s. Maybe I'll use the symbol 2 here. Okay, and that's a little bit easier. So let's go ahead and do that one. Okay, so all 4-digit numbers, here's our 4-digit number. Remember, there's no restrictions except it can't start with a 0. So we have 9 choices for our first digit. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 choices for our second. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And 10 choices for our third. And 10 choices for our fourth. So how many 4-digit numbers are there? There are 9,000. And we need to subtract the number of 4-digit numbers that have 0 2s. So again, let's see if we can count this. So remember, none of these can be 2s. There's no place to put a 2. So how many choices do we have for our first digit? So it's not a 0 or a 2. So there are 8 choices left. So there's 8 choices for the first digit. And for the second, third, and fourth, you're just not allowed to have a 2 here because we don't want any 2s in this number. So there's 9 choices for the second, 9 choices for the third, and 9 choices for the fourth. So we have this many numbers with 0 2s. So that is 8 times 9 is 72. Times 9 times 9 is 81. I'll just do a little multiplication here. 8 times 2 is 16. Carrier 1, 57. We add 5,832. So we subtract 5,832. All right, let's do that subtraction. 8, 6, 1, 3. So there we go. There are 3,168 4-digit numbers with at least 1, 2. I'll use the symbol actually. 1, 2. So again, for this one, it's a little bit more clever because you only have to count one additional thing, is to realize that this at least 1 2 can be reworded to does not have 0 2s. And that way we just have to count one thing, exactly 0 2s, and subtract it from all numbers. Because if you're not counting the ones that have 0 2s, it must have more than 0 2s, so that means at least 1. And that's the trick for this problem. So when you're counting, just be careful in terms of how much work you need to do. So again, you could have done it like this. In fact, it might be a good exercise for anybody who wants to practice. We've done exactly 1. We've done exactly 2. Figure out exactly 3 and exactly 4. Exactly 4 will be very easy. But it should add up to 3,168. And that's a good check that you're doing these correctly. And note that this isn't an arrangement problem in some sense. Or not really, because if we pick a digit for any of our places here, it doesn't affect our choice for any other digit. So that's kind of the key to this.